Okay, so the observant amongst you will have noticed that I'm not Vanessa, who is due to start this presentation, who unfortunately is unwell today. So I'm just going to present the few slides that Vanessa was going to present. You'll have also noticed our fourth member is not visible. He's online. Paul Wilkinson is online. He's recorded his presentation, but he'll be available for questions online at the end of the presentation. Okay, so I shall just begin with an overview of the UK Geoenergy Observatory in Glasgow. And really, it echoes some of the comments that Zoe made in terms of this is a doing facility. This is a real facility in the ground in Glasgow. We're doing research, development, innovation. It's a place where you can go measure, quantify, try, and experiment. There are two images on this slide of where the observatory is located. On the left-hand side, you can see it's in an urban area. It's an area of urban regeneration, post-industrial legacy. So it's very typical of many towns and cities across the UK. And on the right-hand side, a photograph of one of the research compounds, the Fence research compounds, where in most of those compounds, there are 3 boreholes down to different depths. I'll show those in a moment, but there's a lot of monitoring infrastructure that you can see on that diagram, which I'll also explain in a moment. And you can see there a heat center and a heat pump chiller in white. So the observatory in Glasgow is to look at mine water geothermal, that's both heating and thermal storage. Altogether, there are 12 boreholes that have been drilled between 2018 and 2020. The boreholes were drilled, and then since then, geothermal infrastructure has been installed. The boreholes go down to 2 levels of mine working. You can see on the diagram, one called the Glasgow Upper and one called the Glasgow Main. The upper seam is at about 50 metres down, the Glasgow Main is about 85 metres down. And then similarly, there are different depths of monitoring boreholes into the shallow superficial deposits, into the bedrock, and a seismic monitoring borehole, which is deeper at 199 metres. And all these boreholes are unusually instrumented in that they're much more instrumented than you would have on average. And that allows us to really measure and quantify temperature, pressure, and so on in the subsurface as a baseline, and then when we do geothermal work. So the next picture is a picture of the geothermal infrastructure. So it's a schematic diagram. And really the highlight here is that we can use this system in a number of different flexible combinations for either taking heat out of the subsurface, so as you would do on a cold day, or putting heat back into the subsurface for thermal storage, such as you might do in the summer on a warm day. So there are 4 boreholes that are connected up to a series of pipework that go into a heat center, which has got heat exchangers, which is linked to a heat pump chiller. And Andres and Paul are going to discuss results of some of the initial commissioning work that we've done, looking at what happens when you induce change through thermal changes in the subsurface using this infrastructure. And the boreholes, particularly, it's important to understand, can be done in different combinations within the same line working or across different depths of line working. And finally, there's an awful lot of open data that's already available. The baseline data is available on a page from the UK Geos website, where there are things like all the drilling data, the geology, a lot of groundwater data. There's also on the right-hand side of this slide, a lot of the time series data is increasingly becoming available through a page on the BGS website for sensor data. Or you can get that data via an API for the sensor data. So that time series data is also available. So at that point, we're going to hand over to Andres.
Right, thanks very much. So I'm Andres Gonzalez Quiros, hydrogeologist at the BGS, and I'll show you some hydraulic and thermal responses from one of the tests we ran for 25 days at the observatory last November and December. So this test was abstraction in GGO7, so you can see that with the red arrow, 6 liters per second, heat abstraction, so remove of around 3.5 degrees, and reinjection in GJO1, all in the same mine working. So the objective here, so this is not like the typical configuration for a mine water commercial scheme. So the objective here is to create a thermal plume to try to understand better the system, so like a thermal tracer test. So these are some of the hydraulic responses in the mine working boreholes. Both graphs, top and bottom, are the same in terms of the groundwater levels, and the upper graph is with the barometric pressure, and the bottom one with the rain. But there are three things to consider here just very quickly. So first, we can see the Glasgow main boreholes that you can see at the top in kind of green, blue light colors are almost the same levels, and they are higher. So this corresponds to the deeper mine levels. So the water in the deeper mine levels is higher than in the shallower mine levels. So we have an upwards hydraulic gradient. This also shows that there is very good connectivity in the same mine working. However, there is a limited connectivity between the two mine levels, the upper and the Glasgow main. So this is important to characterize the system, and as we discussed yesterday, for the hydrogeological conceptual model. And also you can see some natural fluctuations in responses to the barometric pressure. That is inverted relationship between the changes in the natural fluctuation in the groundwater levels and the barometric pressure. This is normal in confined aquifers. And also some variations after episodes of rain. So this is 10 minutes rain data in the blue bars in the bottom graph. And lastly, you can see in the Glasgow upper lines that you can see the abstraction well is the yellow line. So there is a decrease in the level, and also an increase in GJO1, which is the reinjection borehole. And you can see that the same hydraulic characteristics, it should be like the same one. The changes. However, this shows the injection area or the injection hydraulic properties around the GJO1 are higher transmissivity, so the changes in the groundwater levels are lower. This is some temperature data from the abstraction and reinjection boreholes. You can see in the purple and red lines, this is from GJO7. So you can see that the lines are slightly different. So if you see the purple line is from the wellhead, so it's the water coming up through the pump into the pipes. So the sensor is at the surface. And the red line is the hydrologger sensor that sits above the pump. And you can see the responses are slightly different. And this is because the water is coming up from the mine through the pump and into the pipe. However, the logger that sits above, there is some processes of recirculation there. So this shows that it is important when you design your monitoring network, what you're measuring, and there are different responses. And you can see are quite stable over the length of the experiment. There's slightly decrease at the end, but it's very, very constant around 11.9 degrees Celsius. And you cannot see anything now. And now you see some blue lines, light and dark blue lines that are injection well. So now the logger sits below the mine hole, the injection main. So it fluctuates. You will see why in the one of the next slides from the data from the surface infrastructure, where it varies around 8.9 degrees Celsius. So this change around 3.5 degrees of heat abstraction in the infrastructure. This is some data from the DTS cable. So this is data from the GJO1 that is here and GJO2 that is 10 meters from the injection well. So you can see the change in the temperature over time. You see the more like the blue colors is colder, and you can see the level of the Glasgow upper where the screen interval is. So it's the water flowing into the mine and it's getting colder around 8.59 degrees. And when the experiment stops, you can see more green and yellow colors. There is some kind of recovery of the temperatures around the well. And in the bottom graph, you can see the graph from the GJO2. So you can see the thermal plume also arriving at the level of the Glasgow upper depth, some kind of blue colors there. That is, you can see that after 2-3 days, the thermal plume arriving. And at the right, you have some data at the screen or at the depths of the mine upper, of the Glasgow upper level, some points. So you can see at the bottom, the blue line is very constant. So it's the injection during the experiment, and then the recovery in the purple line. And the other, the yellow and the green is from GJO2 at the level of the mine working. So we can use this data. So my colleague Milan, she's got a very nice poster upstairs. We're trying to use this data to try to estimate the properties and the thermal properties of the different lithologies, because you can see some bands of blue, green, so it's related to the lithologies of the site. And finally, some data about the geothermal infrastructure. So first, you can see here the mine water circuit. So again, you see the orange and purple is the water coming out from GGO7 into the heat exchanger. So that's the purple line. Then the heat is transferred to the secondary loop, and then it's reinjected. So we have the green line, which is out of the heat exchanger and reinjected into GGO1 in blue. Here we have the other side of the heat exchanger, so the temperature in the secondary loop that increases from the light blue into the red. And finally, the data from the other parts of the secondary loop in the heat pump in yellow and light blue.
Thank you. I'm Paul Wilkinson from the British Geological Survey, and I'll be presenting some results from the geoelectrical monitoring systems that we've installed at the UKGeos Glasgow sites. I'd like to begin by acknowledging my colleagues from the Environmental and Engineering Geophysics team, and also from the wider BGS for their input into this work. The imaging technique that we use here is known as electrical resistivity tomography, or ERT. It allows us to make images of the ground between the boreholes of the three sites. Specifically, these images are of the distribution of the electrical resistivity, which is a physical property representing how much the ground resists having an electric current pass through it. The ERT images that we get are useful because the resistivity is sensitive not only to geological variations, but also to changes in groundwater and, really importantly here, changes in temperature. We've developed a system called Prime that lets us use ERT for remote monitoring. It's shown here in this cabinet, and there's one of these systems on each of the sites. It's connected to electrodes that are mounted on the borehole casings. In this photo here, you can see the electrodes that are strapped to the casing and the gravel pack. There are 72 electrodes in the deep holes and 24 in the shallow holes, all spaced at 75 centimetres. The way it works is that we inject a current into the ground between two of the electrodes, and then we measure voltage differences between other pairs of electrodes. We repeat this in different patterns up and down the boreholes, and these measurements are sensitive to different parts of the ground between the electrodes, shown by these diffuse yellow regions. When the electrodes are close together, then we are getting information from regions that are close to the borehole, and when they're further apart, we're looking out to greater distances. The raw data then gets processed and turned into an image of the resistivity distribution in the vicinity of the boreholes, like this one shown here. Now, I've done this at each of the three sites, and these are the images we get. The reds and orange colours, these are higher resistivities, which tend to be associated with sands, gravels, sandstones, and the greens and yellow colours, low regions of lower resistivity, which tend to be more associated with mudstones and clays. And at the Glasgow sites, the mine waste also tends to have quite low resistivity. So those images represent the geological structure, but by making repeated measurements over time, we can also use ERT to monitor changes in the resistivity of the ground, in particular, the heat extraction experiment that was shown in the previous talk, where heat was extracted from water that was pumped out of the Glasgow upper mine working via GGAO7 at site 3, and then the cooler water was re-injected at site 1 via borehole GGAO1. We monitored this process, making sets of measurements every half hour. So this is the baseline image from site 1. We can quite clearly see the mine workings as this band of lower resistivity due to the mine waste. And this image was taken about an hour before the experiment began. Now, if I start the animation. The pumps switch on, and straight away we see this area of higher resistivity, which is indicative of lower temperatures. These temperatures seem to affect the full extent of the screened interval, and they reach the deeper hole on site 1 within a day or so. Now, the magnitude of the changes is pretty much what we'd expected them to be, as resistivity typically increases by about 2% per degree of cooling. We can see some other interesting effects. If I just rewind the video slightly, we have this cooling in the vicinity of the injection borehole. This is probably due to conduction through the casing. And we also get some similar changes in the other hole, which may be due to the heavier fracturing and grouting variations that hole was affected by. Now, towards the end of the experiment, as the pumps switch off, we see a gradual return towards equilibrium, although within the last couple of days, water was extracted from GGA01 for sampling, and we see some changes around that borehole which coincide with that. These will be just coming up here in a second, just this region. Now, the nice thing about the ERT monitoring, it allows us to see processes like heat transport in the ground volumetrically away from point sensors. So it provides a lot of complementary information to the other sensor types that are installed at the site. And I think it's going to be very useful for characterizing the geothermal resource here and identifying potential pathways for environmental impacts. So that's everything from me. So thanks very much for listening.
Okay, so now I'm going to talk a bit about the environmental monitoring programme that's been happening at the observatory. So Andres and Paul showed you the very small changes in temperature and flow that we can see when we do heat changes. But really, I'm going to talk very briefly about a huge amount of work done by a lot of my colleagues around what the baseline of the environment was, the water environment, the gas environment, and the geomechanical type environment. And then just do a little bit of comparison with what we see when we start this geothermal experimentation. And why is that important? Well, yesterday we had a lot of talk about regulation, and clearly all these things are important from a regulatory perspective. But on this slide, I've highlighted a different aspect, which is also the sort of social acceptability. In these old coalfield areas, commonly the shallow land use has been quite complicated. People are concerned about subsidence. So there is a possibility of people being concerned, and we've certainly heard that when we've done stakeholder engagement. You know, they might panic about things, they might protest about things if we don't really understand that baseline environment about how things were before we started doing geothermal work. So the point of, or one of the points from all this work is around understanding that, measuring it, getting that evidence base about what was there before and what was changing anyway in the environment, and then what was changing now. And also another comment that was made yesterday about what's fit for purpose monitoring. What do we really need to do? Clearly at this site, on this diagram, you can see on the picture, we've done loads of monitoring. We've done far more monitoring than you would do for a commercial scheme, and there are a lot more sensors. But understanding which of those are important, you need to measure more to get that answer about which one is important. So I'm just going to show 3 examples of the baseline monitoring. The first one is on groundwater data. So the picture on your left-hand side, the bottom graph with the green and the orange curves, this is groundwater data monitored over a whole year It was the first year that the groundwater loggers were in some boreholes in the mine workings. And basically the main feature of these is you can see overall there's a big curve. That's a seasonal curve. In the winter, the water levels are higher. In the summer, they're lower. But within that, you can see lots of different peaks. As Andres showed, when there's a lot of rainfall or the pressure changes, then we see difference in the water pressure in the boreholes. But then if we zoom in, that small image with the green line, what we see is daily fluctuations or more than daily fluctuations, which relate to earth tides in the borehole. So there's a really complex baseline in that groundwater data. And we need to understand that before we start doing the geothermal work, so that people don't just look at the data and say, it's changing when you're doing geothermal work. And it is changing when we do geothermal work. We can see that on the right-hand side, which is an image. You can see the yellow, the orange and the blue lines are the water levels measured by the hydrogeological loggers in some observation boreholes. And so we're seeing those regular earth tide type variations, daily variations, and highs and lows in those water levels. But there are also two peaks that you can see that stand out. One of them was an abstraction experiment, and one of them was a reinjection experiment. And their signature is really different to that from the baseline. So it just gives that example of why it's important to measure a baseline and to understand the response of to the geothermal experimentation. The second example I've got is around ground or soil gas. Again, this is one of the areas that, for regulatory purposes, it's really important to understand. And so at the observatory, before we started doing construction, there were various surveys of the soil gas, which is the picture you can see on the left-hand side is like a survey grid where different types of gas were measured in the soil. We've also got soil gas probes at some places. So the graph on the right is an example of a soil gas probe data. And again, what you can see is a year's worth of data, and you can see a big curve. The kind of line in the middle, the orangey one, is a temperature. And then the grey and the orange at the top of the bottom are oxygen and CO2. And we've also done isotopic analysis and things on some of these data. And we've now got some scanning lasers on site for near surface air quality monitoring of CO2 and methane. And taken together, all this data on the kind of ground gas, our summary at the moment is we don't see any evidence of mine gas migration. Using some of the isotopic data, for example, you can look at the processes that form the gas, as Angela explained earlier today. We think those variations that you can see are to do with natural photosynthetic and bacterial oxidation processes, which vary by day and by season. And then the final example is about ground motion. So again, in mining areas, either uplift or subsidence related to mining is important. And so some of the monitoring that are at this observatory, so if you start on the picture, which is actually on the bottom right, is a little box called an active reflector, which together with another thing called a passive reflector has increased the precision of the INSAR data, which is how we measure the ground motion using satellite data really, really precisely. The image on the bottom left, you can see those two little reflectors in the area of the observatory at Cunningham Loop. So it's increased the accuracy, and the top left-hand image is how much the ground has gone up or down in a much wider area of Glasgow than the site we're looking at the moment. But the general picture is over a regional scale, the ground isn't going up or down very much in the area. And again, that's really important for us to know. There are some local areas where there is a very gradual decrease in the ground level, but that seems to be due to a widespread area of compressible soils as opposed to mine-related ground motions. So just in this very quick summary about the environmental monitoring, you can see that we've got lots of different types of monitoring in place for before, during, and after geothermal operations. We can really see in some data sets, in some of the water data sets, we can really see seasonal and daily variations. But what we can't see is any evidence of subsurface to surface pathways. We can see evidence of lots of small-scale pressure changes related to pumping, but we understand those processes. And there's also a number of parameters that are really stable before and during the commissioning works of the geothermal operation, so things like the ground gas, the ground stability, and so on. So at the moment, we don't have any red flags for environmental impacts in relation to the geothermal experimentation that people can come and do at the site. And in terms of fit-for-purpose monitoring, I would personally, my choice of fit-for-purpose monitoring for this work that we've been doing is the real key thing is the hydrogeological loggers that we have downhole have been super valuable amongst all the different techniques that we've used for the relative cost that they are. So I shall stop there.